In the previous class, in the discussion that we had regarding the Feynman diagrams, we had just learned how to write down fully interacting Green's function at any order in terms of the non-interacting Green's function. And then preliminary discussion was conducted to write down the Feynman diagrams or draw the Feynman diagrams, and the rules were stated out. Now, we will do the same problem once again. We will rerun that exercise and write down each one of the terms in the expansion of the Green's function in terms of the Feynman diagrams. Just to let you know that we have this one Ck T H prime T1 Ck T prime. This gives rise to a first order Green's function. And similarly, this one gives rise to a second order, and so on. This has to be dagger T prime, and this is second order Green's function, and so on. So, let us write down at least a first order Green's function, and let us write it down the as we have seen earlier. Let us write down a term which is let us write down the first order itself. And so, my H prime give some, so H prime T1 is equal to say half K1, K2 and Q, and now I have two Green's functions. So, it is a two creation and two annihilation operators. So, these are C K1 plus Q dagger C K2 plus Q dagger C K2 and C K1. So, all are all the creation and the annihilation operators are at time T1 as written here. The half factor is included to avoid double counting, and VQ is the strength of the interaction term, which can have some dependence on Q, as we shall see. So, then the Green's function can be written as, now I will write it because it is a first order Green's function, I will write it with a G with a superscript inside the bracket as 1. Now, I will leave this bracket to be filled in later, where there will be terms such as i's, some powers of i's that will come in. I means the square root of -1, and maybe other factors such as maybe -1 etc. that will also come in, but we will try to take that into account. So, there is a minus infinity to plus infinity, and there is the internal time has to be integrated over, and now I have a K1 and a K2 and Q, and I have a Ck time ordered of Ck. So, when I write this now, it means there is a phi 0 which is the non-interacting ground state. So, this is implied. So, it is a Ck of t, then there is a Vq. So, we could have written Vq here as well. So, we can write down the Vq, let's write it here. So, there is a Vq, and then there is a Ck1 plus Q dagger T1, there is a Ck2 plus Q dagger K2 plus Q and a Ck2 T1 and a CK1 T1, and the Green's function, the definition of the Green's function will give me a CK dagger, and that is it. So, this is the first order Green's function, and this first order Green's function, as we, because there are 3 creation and 3 annihilation operators. So, there are 3 factorial terms, which means 6 terms that will be there, and let us just write down the terms. So, the first term we will call it as, so G1, and this corresponds to A. A, as was written earlier, according to certain type of combinations, and as I said that there is some bracket that I am leaving it out and will fill in later. It is minus infinity to plus infinity and a dt1, and there is a k1, k2 and q. There is a minus vq by 2. We have forgotten a factor 2 here, because that came with the definition of h prime. So, it is a vq by 2, and then there is a time ordered product of the non-interacting Green's function. So, this is CKT, CK1 dagger T1, and so this is Q, K1 plus Q T1. This is written somewhat awkwardly. So, this is a Q T1, and then there are this T, C K2 and K2 plus at T1 and K2 plus Q at T1, and then there is a third term which is T with a C K1 T1 and a C K T prime dagger. So, these are the 3 terms. So, this tells that this is equal to, so this is equal to delta k and k1 plus q. This is equal to delta q equal to 0, and this equal to delta k1 to be equal to. Now, there is an inconsistency that I am seeing. So, we will redefine the Green's function. Give me a moment. Let us redefine the Green's function as C k k1. So, this could be, if we redefine the Green's function as the interaction term as, so this is k1, there is a k2 plus q and there is a k2, and there is a k1 minus q. So, that is coming here, k1 minus q. So, then I will have a k1, so that, and then there is a k2 plus q, then there is a k1 minus q. Okay. So, if we redefine the interaction term as this with CK1 dagger and K2 plus Q and K2 and K1 minus Q. So, which means that 2 particles are coming, one with a K1 momentum and the other is K2 plus Q, and then they interact with a vertex which is VQ, and then they go over as a K2 and a K1 minus Q. So, the interaction vertex that retains Q will So, we have just simply redefined the momentum of the creation and the annihilation operators, and in that case the first order Green's function looks like this. And now I will have a term which is not so this is equal to k1, and then there is a k2 plus q, and then there is a k2 there. So, let me write it down a little more neatly. So, this will be T, and then there is a C k2 plus q T1, and then there is a C k2 dagger T1. Now, it is fine. And then there is a C k1 minus q, and then there is a C k. So, this is equal to k1 equal to k and q equal to 0. This is delta q equal to 0, and this is k equal to k1 instead of k1 plus q. So, that is the first term, and this can be written as we will again leave this bracket, and there is a minus infinity to plus infinity, and there is a dt1, and then there is now of course k equal to k1. So, we have the independent variable as k2, q is equal to 0 anyway. So, v q equal to 0 and g 0 k t minus t1. Now, this one, if you see that it is at the same time, and because q equal to 0, it becomes c k 2 c k 2 dagger. Now, what can be done is that I can change the sign of this, and can write it with a negative sign, and can write it with a number operator which is equal to a xi k 2, and then it is equal to a g 0 k. So, these zeros were written earlier as in the. So, this, and now we have k and t prime minus t1. So, how would the diagram look like? So, this diagram, this particular diagram would look like there is a line which is from t prime to t, there is a momentum which is k. Now, at t equal to t1, I have an electron bubble which is momentum k2, and it at t equal to t1, and then it continues as k. So, you see that this term, let us write it with a different color. So, this term is here, this term is this bubble, and then this term is here, okay. And the v q equal to 0. So, this is q equal to 0, q equal to 0, and that is the. So, this is v q equal to 0 is the wiggly line. So, we have two Green's functions as non-interacting Green's functions. There is a number operator, or rather there is a bubble, electron bubble, which corresponds to this n xi k 2, and then there is a g 0, which is again the unperturbed or the non-interacting Green's function, which is taking it from t 1 to. So, this is equal to. So, in fact, so there is a t prime to t 1 is actually. So, we should do it this labeling properly. So, this is these labeling has to be. So, this corresponds to the green term, that is the last term, then this corresponds to the first term, and then this is a bubble. So, this is the full description of this, and we will have to evaluate. In order to evaluate this diagram, we will have to compute the integral that is appearing, which we are going to do in a short while from now. But let us all I mean write down all these terms which we see here. Then of course, there is a term, let us call a G 1, G 1. Now, it is a B. So, that looks like again minus infinity to plus infinity dt 1, and then sum over and then we have a V q by 2, V q by 2, not sure whether we put. So, there is a half factor that will come out. So, there is a half there, and so there is a V q by 2, and now there will be T C K T C K 2 dagger T 1 and T C K 2 plus Q T 1 and C K 1 dagger T 1, and there is a T C K 1 minus Q T 1 C K dagger T prime. So, this corresponds to a Green's function, this corresponds to another non-interacting Green's function, and so there are 3 non-interacting Green's function, and this term can be written as so this term is equal to, so there is a line which goes from T prime to T, and so there is a time T 1 and so this is k, and this is equal to k 1, and this is equal to k again, and there is this term that goes from. So, this is really the term that is there. So, I mean this is really T 1, which means that these two T 1s, though they look different, they happen at the same time. So, there is an instantaneous interaction, and the vertex carries a finite momentum q, and so again let us do this color. So, this color, the green color that we see, is a non-interacting Green's function that propagates from T prime to T 1 with a momentum that is k. So, because k equal to k 1 minus q, and then there is a Green's function that propagates from. So, then there is a red one that is here, that is. So, that talks about a Green's function which goes from T 1 to T 1, but with a momentum that is equal to k 1. So, k 1 equal to k 2 plus q, and similarly the other one has this one is here, which goes from T 1 to T, and the vertex V q now carries a q, a momentum q which is not equal to 0. So, this is B. So, let us take the third term. So, G 1 C, that is equal to again this, and it is a minus infinity to plus infinity, and we have so there is a dt 1. So, there is a dt 1, there is a sum over, there is a V q over 2, and now I have terms such as T C K T C K 2 dagger T, T C K 1 minus Q T 1 C K 1 dagger T 1, and there is a T C K 2 plus Q T and C K dagger T prime. So, that tells me that this gives me delta k equal to k 2. This of course gives me that So, this is delta q equal to 0 and this is delta k is k 2 plus q. So, those are the three terms. Now, this is written as again a line like this, and then so there is a this term is like the first term where we have a t prime and a t here, and now this is propagating with k, this is again propagating with k. This is that V q equal to 0 and this is that k 1 which is happening at t equal to t 1. So, that is the so again the last term corresponds to the Green's function, the free Green's function in the so showing it once more. This is here, this is here, and this is this one. Okay. So, that is those are the three terms that appear here, and likewise we can write down G 1 d. We are doing it all of them separately, such that you get a feel of these things happening there. So, G 1 d which is equal to again bracket and then minus infinity to plus infinity and a dt 1 sum over the internal momentum. So, there is a V q and then there is a t c k t and a c k 1 dagger t 1. So, t c k 1 minus q t 1 c k 2 dagger t 1 and t c k 2 plus q t 1 and c k t prime. Again that this gives me delta k and k 1, this gives me delta so k 1, so this is equal to, this gives me delta k and k 2 plus q, because k 1 is equal to k. So, and this is equal to delta of so this is k 1 minus q equal to k 2, k 1 minus q is same as k 2, and this is delta k 2 plus q k, and this is again written as t prime t, then there is a vertex which is with q, and this is k 2 and this is t 1 and this is t 1. So, this the last term is the Green's function on the left, and then there is a term which is the vertex is carrying a momentum q, and there is a free electron that propagates from T 1 to T 1 with momentum k 2, and then it again carries on with a momentum k from T 1 to T. Those are the three terms. Similarly, let me write down for completeness G 1 E. Now, this is something that is important, you should see it. So, then this is equal to again that bracket and then this d t 1, then there is a summation and then there is a V q. Now, you have a C k t. These groupings were discussed earlier, and we were going by those groupings that we have numbered them as A, B, C, D and so on. So, this C k dagger T prime. So, C K 2 plus Q T 1, C K 1 dagger T 1 and T C K 1 minus Q T 1 and C K 2 dagger T 1. So, this tells me that so there is a free Green's function that propagates with a momentum k from T prime to T. This one tells me that there is a delta k 2 plus q has to be equal to k 1. This one says that delta k 1 minus q has to be equal to k 2. These two momentum conservation means the same thing. So, this can be drawn as this. Now, this is a disjoint from, so there is one that propagates from, so it is like this and then it is like this. So, there is one that propagates with k 1 and there is a, then it propagates with, we can do it. So, there is this way, this propagates like this and then there is a wiggly line V q which is equal to here. So, this is k 2, this is T prime, this is T and this thing is happening at T 1, but these two are disjoint. You see that there is the Green's function that takes from k 1 to k 2 plus q. So, this is that k 1 to k 2 plus q and then there is a k 1 minus q going back to k 2. So, this is that the two Green's functions are shown on top and bottom of that shell like structure and the wiggly line in between will be the V q which carries the momentum, the interaction term that carries the momentum. So, this is k and the last term is G 1 and F which is again equal to minus infinity to plus infinity and a dt 1 sum over and then there is a V q by 2, forgetting this 2, but does not matter for drawing the diagrams, but for getting the final answer this factor of 2 will be important. T C k T C k dagger T prime C time ordered C k 2 plus q T 1 and a C k 2 T 1 dagger then T C k 1 minus q T 1 and a C k dagger T 1. So, you see again this Green's function propagates without any interaction or rather without any disturbance from T prime to T. So, we will have to write that. So, there is a T prime to T goes with k. Now, there are two. So, this corresponds to delta, I mean the q equal to 0 and this also corresponds to delta q 0. So, I have two electron bubbles which are like this and they are connected with a q. So, one of them is k 1, the other is this is at some intermediate time that happens and at k 2. So, these are this is the Feynman diagram for this particular case. So, now you see let us just go back once again. We have a Green's function with a bubble, this then there is a Green's function which there is an interaction vertex which carries momentum q, then again this is a Green's function and bubble, then again a Green's function with a vertex carrying a momentum q, there is a disjoint diagram, there is a disjoint diagram. So, if you summarize So, there are two terms which look like this. Then there are two terms which look like this, and then there are two disjoint terms. One of them look like this, and the other one looks like okay. So, now let us see some higher order diagrams, some typical higher order diagrams. So, we can have a term like this. So, a higher order diagram, as you understand that we will have two vertices. So, two wiggly lines at least, I mean that is the second order diagram. A third order diagram will have three wiggly lines. So, it is one of them, then there is one like this. Then there is one like this. Then there are so then there is one term like this. So, anyway, we have two wiggly lines, and we can have a term like this. Which is a disjoint diagram. So, of course, these are the last three are disjoint diagrams, and then there are joint diagrams, and this and so on. There will be many of them. I have just shown some typical second order diagrams. So, we can in principle write down any order for the diagrams. Now, we just have to write down the corresponding expressions for that, like the first one, let us if we call it as 1, will include an integral, and then there will be two time dt1 and dt2, and then there will be a g0, g0 and 3 g0s, and there will be a vq1 and a vq2, and then there are two electron which are probably xi k1 and xi k2, just roughly writing down. So, that is the first term. So, 1 will have the form. So, notice that these diagrams are identical, and similarly these diagrams are identical, and so on. So, there are ways to actually find out such symmetries in these diagrams, and I mean calculating one diagram and then multiplying it with the number of such similar diagrams will actually one does not have to compute those many diagrams as actually that come in. Let me give you an example, the symmetry. So, consider a typical third order diagram. So, I have 3. So, there is a Q3, there is a T1, there is a T2, there is a Q1, there is a Q2 and so on. And then there is a T prime, and then there is a T and okay. So, so these are that is a typical diagram. So, then there is a T3 here, T3 at this, let me write it down neatly. So, there is a T3 here. So, now if we permute between T1, T2 and T3, they give rise to the same diagram. So, we will have 3 factorial such diagrams. In any case, I mean the when we consider a third order diagram, we have a third order diagram has 7 creation and 7 annihilation operators. So, how many combinations we are going to get? 7 factorial combinations. And how many of them are? So, this is equal to 5040 combinations. This tells that actually we do not have to calculate all the 5040 diagrams. This permuting between T1, T2 and T3 correspond to 3 factorial diagrams. So, which means that corresponding to those 3 factorial, which is equal to 6 diagrams, you have to only compute 1, and similar such symmetries can actually be understood or deciphered. And so, all these things will look the same, and in fact, if you think about it, that there are so you calculate one diagram, and according to the symmetry you multiply it by n factorial of each one of those diagrams, and but there is also a n factorial in the denominator which cancels. So, all these will only correspond to one diagram corresponding to the symmetries that you find. Now, we will talk about what we have been leaving out is the multiplicative factor in the perturbation expansion. So, see how the multiplicative factors expansion. And what I mean is that what we were writing as this and we are leaving it out, actually there will be, so there are, so 2n plus 1 creation operators in the nth order. So, there will be 2n plus 1 creation operators and 2n plus 1 annihilation corresponding to the nth order. So, so there will be 2n plus 1 non-interacting Green's functions. So, we will have, so each of the Green's function will have a factor of I. So, there will be a I into 2n plus 1, because each one of those CK dagger it is equal to I GK. And then we will have to multiply it by a minus 1 whole to the power n. This comes from the factor in the S matrix expression. So, this you see that the S matrix expression also has a factor expansion. This has a factor of minus I to the power n, and there is a minus I that comes from the overall interacting Green's function, because G equal to minus I and then the time ordered product. So, if you multiply all that, it becomes I to the power n. So, typically nth order Green's function will have I to the power n. Since we were talking about a first order Green's function, then we should have a factor of I in each of these cases. You can put this factor of I and so on. But that is not the end of the story. There is another thing that comes in, that is a plus minus 1 term or minus 1 whole to the power f, where f is the number of fermionic loops. So, how do we understand that? So, we have a term which is like this and so on. So, this corresponds to T CK1 dagger, CK2 dagger, and then CK2 plus Q, CK1 minus Q, and then CK dagger. I am not writing the time indices explicitly. There is this, then there is this. So, if we change the order of this, this brings in a minus 1, and then of course, this remains as it is. So, now this, so basically this corresponds to delta Q equal to 0 and one of the fermionic bubbles. So, we get a minus sign. Look at this other term. So, this was the term A that we have written. The number B is this, and so this is equal to T CK1 dagger, CK2 dagger, CK2 plus Q, CK1 minus Q, CK dagger, and so on. Now, there is so this one has to, so this will be one sign, this will be another sign. So, a factor of plus 1 that is twice minus 1. So, anyway, one has to keep a track of how many swaps one makes, and each time there is a bubble, you are sure to get a minus sign. If there are two bubbles, then one gets a plus sign here. So, let us talk about the disconnected diagrams and see what they contribute. And these diagrams are called as the vacuum polarization graphs. So, at each order of the perturbation theory, all the prefactors that we get while doing the expansion, they are all multiplicative. So, there is a numerical factor that n factorial, which comes from the symmetry of all the diagrams, they cancel with the denominator, and we have a factor of I to the power n, and a plus minus 1 depending on how many fermionic bubbles we have, and this means that the diagram actually factorize as take an example for example of a second order diagram. So, this is a disconnected second order diagram, and this can be easily understood that this does factorize as a term which is this and multiplied by with the term which is this. So, in general, this plus this and then a bubble like this and plus this and two bubbles like this and so on can be written as so this is equal to a term like this and then multiplied by a term which is 1 plus this kind of a plus there are bubbles and so on. But remember, this is nothing but the denominator which is equal to S infinity minus infinity. So, this cancels exactly the second bracket or the second bracket cancels exactly with the denominator. So, from this factorization it is clear that only the connected diagrams survive. Now, this is a big simplification because this simplification tells us only the connected diagrams will have to be computed and we really do not have to compute terms such as these ones or these ones or these ones and so on. So, the top diagrams will be good enough to calculate and we can do away with that. So, now how to compute? We have not still yet done the integrations over the time. So, one important thing is that one has to integrate over internal energies and sum over internal momenta. So, then each of the Green's function is written as, which is I am writing it now in the k omega space, it is equal to 1 minus psi k and a plus I eta k, where eta k was shown to be equal to a sine of this. So, a second order, a typical second order diagram which is equal to like this and this and this. So, there is a q 1 and omega 1, there is a q 1 omega 1. So, this is omega 2 minus omega 1 k minus q 1 and this is k omega and so this is q 2 minus q 1. So, q 2 minus q 1 and so on. So, these are k omega. So, that diagram has to be written now, it is a second order diagram. So, we should put a I square and then there is a d omega 1 by there is a 2 pi normalization that one has to use and there is a d omega 1 there is again a 2 pi that has to be used and there is a v q square and then there is a sum over q 1 and q 2 and then there is a g 0 square k omega and a g 0 k minus q 1 omega minus omega 1 and g 0 q k omega 2 g 0 q 2 minus q 1 omega 2 minus omega 1 and so on. So, these are the there is a loop that is forming and this loop will give rise to a minus 1. So, this one has to calculate with this g 0 etcetera put there and then do a method of complex integrals which you must have seen in complex mathematical physics course under this complex analysis and complex integrations, and that has to be done and then one has to evaluate these integrals accordingly. And that will give us the full Green's function evaluated at a given order. For example, in this case we are evaluating it at the second order.